On to Newton's second law. And Newton's second law is useful whenever we notice any of our hints that we're dealing with a force problem. Whether that's a force being explicitly mentioned, like friction or drag or thrust or springs, anything like that, we have a set method that we're going to use to solve these types of problems. The first thing is to draw that free body diagram, even if it's not for points. Make sure you have it, so that way you have exactly what you need to know. Make sure your arrows are going the right way. You can do the proper Newton's second law equation, because the second step for solving forces is the second law. The forces that make it go minus the forces holding it back equals mass times acceleration. Or Newton's second law for rotation, the torques going counterclockwise minus the torques going clockwise equals I alpha. Remember that we need to treat forces in the x and y direction completely separately, just like we would for velocities or accelerations or displacements. In equilibrium, this means up pieces equal the down pieces and the right pieces equal the left pieces. This also means that there is zero acceleration. Remember that F does equal F. So there are certain instances where you can relate any two forces. Frictional force equals the weight force. That may be useful. The slope of an MV versus T graph is F, or the slope of a P versus T graph is F, lowercase p for momentum. This is the impulse momentum. Forces are vectors, so watch your direction. Apparent weight is your normal force. If your normal force is greater, you're going to feel heavier. Like if you're in an elevator moving up and slowing down, you're going to feel heavier. Or at the bottom of a roller coaster loop. Greater normal force, so we feel heavier. A scale gives you the reading of that normal force. Ideal pulley means it's massless and frictionless. If a pulley does have mass, we're going to use Newton's second law for rotation to find A using alpha equals A over R, and then stick that A into our translational Newton's second law. If you see the phrase rough surface, that means there's friction. Smooth surface means no friction. Friction always opposes sliding, not motion. Friction always opposes sliding or the direction it would be sliding if you replace the surface with ice. Static friction is your max friction. Whenever you see a request for a maximum amount of friction or minimum coefficient of friction or the critical angle, any of those limit questions, we're going to set whatever it is we're doing equal to 0. So it might be your weight force minus your frictional force equals 0. So mg minus mu Fn equals 0, and then you can solve from there. Just remember that maximum, minimum, critical, we're going to set those things to 0. Static friction must be overcome before sliding is going to happen. Tires need static friction, or spheres need static friction to generate the torque about the wheel's center. If there is only kinetic friction on a surface, then there's going to be sliding. There's not going to be rolling. Spring force for a Hookean spring, Fs equals negative kx. Two springs next to each other, like this. We're going to use our effective spring constant K1 plus K2. That's a physics C thing. And if they're in line with each other, where they're connected on top of each other or side by side, we're going to use the inverse of our effective spring constant equals the inverse of K1 plus the inverse of K2.